Very good morning to all of you. So today, as I mentioned in our previous class, we are going to start off with a new topic, that is regular expressions. So see, basically we are done with almost all the portions of finite automata regular language. The only portion that is left is regular expression, which is a very important portion rather. So basically we use regular expression to represent a regular language, just like that a DFA can be used to accept a regular language, or a regular grammar is used to construct or design a regular language. In the same way, regular expressions can be used to represent a regular language. Okay. So what we are going to do today is we are going to see that what are the various rules of constructing a regular expression. Yes, we do have some fixed rules using which we need to work with regular expressions. So we need to know those rules, and we have some identities associated to regular expressions. So we need to know those identities. We have some theorems that we should know. And after we are done with all these things, later on we will see how to transform a given DFA into a regular expression. Okay. Or maybe a DFA will be, a DFA is given and you have to construct a regular expression for the same, right? So again, the reverse is also important. So we'll see the both the things. So let me share the screen. Before I start, let me tell you, this is direct from the book that I have suggested all of you to refer, which is Mishra Chandrasekharan. So if you open chapter number 5, you will see that we have regular expressions over there. Okay. So these are some of the points that we must know regarding regular expression. So we give a formal recursive definition of regular expression over the alphabet set as follows. See, you won't be asked to define a regular expression ever, but you should know these things. Okay. So any terminal symbol, by now I'm very sure all of you know that what is a terminal symbol. So any terminal symbol that is an element of this alphabet set, or a null or a lambda, are regular expressions. These are themselves regular expressions. Okay. When we view A in a lambda as a regular expression, we denote it by A. So while writing, just to differentiate between when am I writing a normal part of a language or a string A, and when am I denoting it as a regular expression, this differentiation is used. Just as you can see, this is written in a bold font and this is used in a regular font. Okay. So bold font denotes a regular expression, that A is a regular expression. Meaning is same, right? Both are A, but one is being a part of the language, which is written in normal font, and one is being a part of the regular expression, which is written in a bold font. Okay. Next, the union of two regular expression, maybe if we name the two regular expressions R1 and R2, then the regular expression, the union of the regular expression will be written as R1 plus R2. The concatenation of two regular expression is written as R1 appended with R2. Just write them one after another. Okay. The iteration of a regular expression R is written as R star. So this is quite similar to your closure. It is actually the same thing as closure. So closure of a regular expression R is written as R star. Okay. If R is a regular expression, sometimes we also use a first bracket to represent the same thing. That representation is also a valid representation. So if R is a regular expression, then capital R inside first bracket is also a regular expression. Okay. So a regular expression over an alphabet set can be precisely obtained by recursively applying all the rules from 1 to 5. Now see, if we have a regular expression, it must be constructed using one or the other of these 5 rules. No regular expression can be constructed without any rule outside this 1 to 5, right? So anything and everything that we are designing as a regular expression must follow one of these rules, or maybe multiple multiple rules out of this point number 1 to point number 5. Okay. This is an important thing that you must know, that in absence of parenthesis we have the hierarchy of operation as follows: iteration, concatenation and union. So sometimes if you are dealing with regular expression and you need to evaluate a regular expression, just like we evaluate an arithmetic expression, we basically use exponent and then multiplication and then addition. Similarly over here also the hierarchy goes like: we first evaluate the iteration or closure, then we go for the concatenation, and finally we go for the union part. Okay. So these are few examples. Let me show you very basic examples. So if for example a comma b is an element of alphabet set, then a denotes the set A. So this is the language, this is the regular expression. Again, this is the regular expression, this is the language. The language consists of a comma b. Similarly, the same thing when represented in form of regular language or in terms of regular language will be a plus b. ab, ab. ab will be within curly braces. This is a language, normal language. This is the regular expression. Again, the language a, closure of a, what do we write? We write inside the second bracket we write lambda, then a, then aa, infinity, up till infinity. Same thing is represented in using regular expression like a star. This representation you all have seen previously also. I have used it multiple number of times, right? And again, this is also important when we are taking the closure of a comma b, like any possible combination of a and b with repetition is possible. If this is the language, then the corresponding regular expression for the same will be a plus b star. Okay. Now this language is any combination of a b is possible. The same thing in regular expression is a plus b star. Okay. Now these are the few things, few very easy examples, very basic examples. Now a few more examples are here. So describe the following sets by the regular expression. So these are the languages given to you. You have to just represent them in terms of regular expression. So this is very straightforward and easy. So if 101 is your language, then the regular expression will be just 101 written in a bold font. Similarly, ABBA, if it's a regular expression, if it's the language, the regular expression is going to be ABBA in bold fonts. Again, 0110, if this is the language, then we can just write this like this: 01 plus 10 in bold fonts. This will be the regular expression. The set lambda comma ab, this will be again written as lambda plus ab. ABB comma A comma B comma BBA, anything can be there inside curly braces. Just write them using the plus sign and bold font. Okay. This one again, this is the closure of 0. So just write 0 star. Okay. This one is a bit different. Look at this: 1 1 1 1 1 1. So we do not have a lambda over here. I have told you about a positive closure, that is 1 plus. But we are not directly using the the symbol plus in case of regular expressions. What we do is we present it in this form, that is inside the bracket we have 1 star, that is the clean star of 1, and outside that we have 1. Why? Because there is no lambda. So inside bracket we have lambda comma 1 comma 1 1 comma 1 1 1, and then we have an extra 1 outside, which when concatenated will always give 1, then 1 1, then 1 1 1. There won't be any lambda. So anywhere if you get a language like this or a set like this where it starts with at least a single occurrence of the symbol, then in the corresponding regular expression you have to write the symbol followed by the star of the symbol, which I used to write as 1 plus. We do not use that plus symbol over here for positive closure. Instead, it is written or represented in this form. Okay. So I don't think up to this there is there should be any problem, because these are very easy things. So proceeding with that, you have to next question.
Ma'am,
Yeah.
how will we represent these bold things on paper, like
Yeah,
while
I was
writing?
also thinking the same thing. What you can do is you can just double overwrite whatever you are writing. Like try to just deepen the thing whatever you are writing. I think no other way is there to represent it when you're writing in your answer scripts. Write one in a normal way, and when you are writing it for a regular expression, just overwrite it once or twice so that it becomes deep. Okay.
Okay.
So next is describe the following sets by regular expressions. L1 is equal to the set of all strings of zeros and ones ending in 00. The same thing you have seen for a language, you have designed a DFA for this, you have seen for a grammar. The same thing now for regular expression. So you have to design the regular expression for the set of strings.
0 plus 1 asterisk
Yeah,
0 0.
exactly. So we can just write 0 plus 1 star, because we can have any combination of zeros and ones, and it must end with 0 0. So any combination of 0 and 1 will be 0 plus 1 star, and then ending with 0 0, this one will be there. Okay. Next is a set of strings of zeros and ones beginning with 0 and ending with 1. Okay. So again
0 0 plus 1 star 1.
exactly, beginning with 0 0, ending with 1, put a 1 at the end, and in between we can have anything. So having any combination of 0 and 1 means 0 plus 1 whole star. Okay. Next we have L3, which is lambda.
1
Yeah,
star.
lambda comma 1 1 comma 1 1 1 1. So this is nothing. If you look at this carefully, this is nothing but 1 1 star, because everything is like occurring in a pair of ones. So we can just simply write it as 1 1 star if you look at this. Okay. So now we can move to some identities associated to regular expressions. Some rules and some identities which you should always remember related to this regular expressions. Okay. First is epsilon null plus r is equal to r. Null r concatenated with r, or r concatenated with null, will always give you a null. Okay. Lambda r lambda is going to give you a see, look at this difference. Okay. So do not get confused. Generally in MCQ you might get a question of this type. So when it's lambda, it's r, it's lambda concatenated with r, it's a r. But when it's null is an empty language in itself, and lambda is a language with a whose length is empty. It does not have any length, that is lambda or epsilon. And null is something, the language itself is a empty language. Okay. So empty language with r will give you empty null, but a string or a language whose length is zero length, or so you can write lambda also, epsilon also, that would give you a r. Okay. Again, a lambda star will give you lambda, null star will also give you a lambda. R plus r gives a r. R star concatenate with r star gives you r star. R star is equivalent to r star r. You can write it in both way. Associativity is there. R star whole star is same as r star. Okay. Lambda plus r star is equal to r star. So this is very clear, because see, r star is basically everything which is there in except lambda. If you remember, we have just seen over here. Wait, where was the thing? Over here. Yeah. So here was the thing where we see that 1 star is nothing but any we can represent the language like this. It starts with 1 1 1 and 1 1. So it doesn't have lambda. So if this is r and this is r star, so r star plus lambda would give you 1 star, because lambda was missing over here, and if I add a lambda it will be nothing but 1 star. That is what is written over here. R star plus lambda will give you an r star. Okay, or you can also write it in the other way out, that is lambda plus r star and then r. This is the same thing. Okay, next is pq star p is equivalent to p qp star. These things you have to remember. Okay, so pq whole star p is equal to p qp star. Next is p. This is a very very important identity which you will be using in many proofs. You will be requiring in many proofs. P plus q whole star is equal to p star q star whole star, which is again equivalent to p star plus q star whole star. So this single thing can be written in this way also, can be written in this way also. Okay, that is p star q star whole star, or p star plus q star, the entire thing whole star. Okay, next identity, p plus q whole concatenated with r is pr qr. It's easy, and again r p plus q is rp plus rq. These are easy. The two things I think you should remember, three things, the three identities specifically you should remember is I9, I10 and I11. These are very important, which you will be requiring multiple number of times when you deal with certain problems of regular expression. Okay, a very important theorem related to this regular expression is Arden's theorem. Okay, so Arden's theorem says that let p and q be two regular expressions over sigma, and if p doesn't contain lambda, then the following equation in R, namely R is equal to q plus rp, has a unique solution, and only one and unique solution, which is actually one and only one solution, and that solution is R is equal to qp star. So basically p, q, r, these are regular expressions. This is a expression given to you, r is equal to q plus rp. The Arden's theorem says that if this is the expression, or this is the equation rather, and p, q, these are regular expressions, then this equation has a unique solution. And what is the unique solution? The unique solution is r is equal to qp star. Okay, so we actually have the proof of this Arden's theorem in our syllabus. So I'll just open the canvas and try to prove both the parts. There are two parts. If you look at the statement carefully, one is that the solution for this equation is r is equal to qp star. The next part is this is the unique solution. So both the things should be proven. Okay, so let me just go to the canvas. So we are given with the equation r is equal to q plus rp, right? Now what we can do is, we can just write q plus, replace r with the solution that is provided. What is the solution provided to us? qp star, right? R is equal to qp star. This is a solution which Arden's theorem actually says that R should have. So what I do is I just put qp star over here. Okay, and p would remain same. P will be same as it is. Next, what I can do is I can take q common, right? And this would give me epsilon plus p star, or I should not write p star, I should write p star p. Okay, Now what is epsilon plus p star p? We had just seen the identity. If you remember,
P
it's
star P.
actually p star. That is epsilon plus p star p is equal to p star. So I'll just put q p star over here, and what I get is the value of r is q p star. That is the assumption with which we had started. Okay, so this proves that this is one of the solutions. Like r is equal to qp star is one of the solutions. Now we need to prove the second portion also, that this is the unique solution. Okay, so for that, again let me rub this part. We start off with this equation. In the next line, what I do is I replace the occurrence of r with q plus rp. What is the value of r? R is equal to q plus rp. So what I can do, I can replace this r with q plus rp, right? Won't be a problem. So it gives me q plus qp plus rp square. Next, I do the same thing. Q plus qp plus q plus rp p square, and I get q plus qp plus qp square plus rp cube, right? Achha. Now if you keep on doing this, what you get is q plus qp plus qp square plus continues up to qp to the power n, and for this portion we can write r p to the power n plus 1, because if this is n, this would be n plus 1. Okay. Next, can do is q plus qp plus qp square. These are q, okay, sorry for the qpn. For r, replace r with qp star. Replace r with qp star, that was a solution given to us. Then pn plus 1. Okay, now if you take q common, it will give you lambda plus p square pn plus p star pn plus 1. Okay, now this entire thing is nothing but p star. This entire thing, if you look at it carefully, it's nothing but p star. Okay, and at front we had a q, so finally again we get q p star. We had started with this again and we have ended with again r is equal to qp star. Now finally, after doing this, we can say that qp star is the unique solution. So first we have proved that it is one of the solutions, and next we have proved that this is the only solution that we can have for R. Okay, and the value is QP star, that is the assumption with which we had started, right, QP star. So this was the proof for your Arden's theorem. So like, is the proof clear to all of you, or do I need to explain it once more? All of you, is the proof clear to all of you?
Yes, ma'am.
Okay. So let's get back and see what else do we have. Okay. So you might be given questions of this type. So read the question. So we have given a regular expression for representing the set L of strings in which every 0 is immediately followed by at least 2 ones. Okay, prove that the regular expression lambda plus 1 star 0 1 1 star 1 star 0 1 1 star whole star also describes the same set of strings. So the question has two parts. The first part says that you have to find the regular expression for representing a set of strings in which every 0 is immediately followed by at least 2 ones. So first let us solve the first part. Okay, so every 0 is immediately followed by at least 2 ones. Okay, so what we can do is, see, if we have a 0, we must have 2 trailing ones. If we do not have a 0, we can even have a single one, because for a single one no constraint is given. It's said that if we have a 0, it should be followed by 2 ones, but it's not mentioned what should be the thing if we have a single one. So we can design the regular expression in this form, that it can be either a 1 or a 0 1 1 and any combination of this. So we can have a 0 followed by 2 ones, or we can have a single one and we can have any combination of this. Okay, is it clear? Is the logic clear? Why is the regular expression being designed like this?
Ma'am, could you please repeat?
Yeah, so the question tells us that we have to design the regular expression for the set L of strings in which every 0 is immediately followed by at least 2 ones. So if there is a 0, there should be 2 ones after that. Okay, but the constraints do not tell you anything about what will happen if I have a 1. Like if I get a single 1, what will happen? It says that when I get a single 0, it should be followed by 2 ones. But what if I get a single one? Nothing is said, right? So we can have any combination of 1. That means that is how I am thinking, and I am designing the regular expression. So for the constraint part, 0 immediately followed by at least 2 ones. So I have 0 followed by 2 ones, and I can again have a single 1, any combination of 1. So 1 or 0 1 1 and like any combination of these. Clear?
Yes, ma'am. Okay.
Look at the next part. Prove that the regular expression R is equal to lambda plus whatever it is written, a big part, is also describing the same set of string. So basically what you have to prove is this is equal to this, because this already you have designed the regular expression, and question number 2 is asking for you have to prove that this regular expression also describes the same set of strings. So what we can do is we can start off like this, that is if you look at this, see, look at the trend of this equation. It's 1 star 0 1 1 star, and then again 1 star 0 1 1 star whole star. Okay, so if this is R, we can write it like lambda plus R star. Okay, so that is the thing I have written over here. R is equal to, instead of R they are using P1, so lambda plus P1 star, where P1 is 1 star 0 1 1 star. See, again go to the equation. P1 is 1 star 0 1 1 star. So the expression of the equation becomes lambda plus P1 star. Okay, so that is what I have written over here. Lambda plus P1 star, which is nothing but equal to P1 star according to identity 9, and P1 star, again just replace whatever value we have taken for P1, that is 1 star, 0, 1, 1 star, and there is a whole star for this. So we can just write it like P2 star, P3 star, whole star. If 1 is P2, 0, 1, 1 is P3, so we can write it like this: P2 star, P3 star, whole star. Now again, coming back to this identities, we have seen this. If this is P2 star, P3 star, whole star, it can also be written either in this way or in this way. So here what will we be requiring is writing it in this form. This is P2 plus P3 whole star. So what is P2? P2 is 1. What is P3? P3 is 0, 1, 1. So P2 1 plus P3 0, 1, 1 whole star. That was the regular expression we had designed. So if we start with this, we ultimately prove that this one is equal to, or we are evaluating this one equal to 1 plus 0, 1, 1 star. Hence proved. Okay. Any difficulty in understanding that how am I proving that this is equal to this thing? Everybody understood? Everybody understood, right? I need not repeat.
Yes, ma'am.
Okay. Okay. So we have few more examples, and what we will see mainly in our next class is, wait, let me show you. We'll start off with conversion of this a DFA or an NDFA, whatever is given to you, to equivalent regular expression. Okay, so that is the thing we are going to do. Sorry, not that part, this one, algebraic method using Arden's theorem. So we will be given a transition system, maybe an FA or a DFA, and we will find out the corresponding regular expression for the given transition system. Okay, that's the main thing we are going to focus in our next class, and obviously one or two more proofs, like more such problems I am going to show you, like the one we have just done right now, that is some value will be given for LHS and something will be given for RHS, and then you have to prove that LHS, just like this, that proves this one is equal to this one. This is a very common kind of a question in context of regular expression. So we'll be solving more such examples, and we'll be seeing what are the different identities we generally use for solving these kind of problems. Okay, so this was all for today, students. Thank you so much. If you have any doubts, please ask. Otherwise, you can one thing, you have the two examination codes, since section A and C both are here. So I'd request someone from A and someone for C, please check whether the examination codes are working properly and confirm the same.
Yes, ma'am, they are working.
Working, ma'am.
Thank you so much. Thank you.